All right, everybody. Hey, this is Mr. Harvey here. Let's get into chapter 6 and let's continue our lecture from our previous class. So when we last met, we talked about the causes of the scientific revolution. We talked about what the previous medieval kind of viewpoint was. Remember, very much based on Aristotle, religion, Ptolemy. Those were their main lenses of how they viewed the world. And then we got into Copernicus and some of our main thinkers. So let's talk about Copernicus and let's review Copernicus a little bit. So Copernicus, right, one of our first thinkers of the scientific revolution, really important. And remember, take a look at when he was born. Born during the Renaissance, lived during the late Renaissance, the end of the Renaissance, and the Reformation. And so this gives us an idea that the Renaissance, the Reformation, the scientific revolution were all melded together and building off of one another. We're not necessarily building off of one another, but the Renaissance, helped create the Reformation leading up to and helped building and creating our scientific revolution. So Mr. Nicholas Copernicus, let's talk about him. Let's review. All right, remember, Polish priest, a good Catholic. And this very much influences his decision to publish his very influential foundational text on the revolutions of the heavenly spheres, a book that we need to know, to publish those on his deathbed because he was super, super, super fearful of the backlash that he was going to get, not just from the Catholic Church, not just from Protestants, but from society as a whole. And he was that intimidated about that. Because being ostracized from life, he could be killed for that. He was worried about that. And so he published his text on his deathbed. Also, he published a preface in his text directly addressed to the Pope, where he states why he is putting forth this heliocentric ideology, and also states that, hey, some of my ideas are not new. They're actually older, ancient ideas. And he references Greeks and Romans within his ideas that are not the norm. But as we've just discussed, the main ideology that he is confronting is geocentrism that is based on Aristotle's viewpoint. Let's continue, okay? And so his ideas, ladies and gentlemen, his book is going to just launch this newfound movement of empiricism, logic, rationality, and questioning this traditional geocentric viewpoint of the universe. Okay? And what did he believe? Heliocentrism. That is what he is putting forth. He is putting forth this idea that the sun is the center of the universe, not a solar system yet. We're not quite there yet. And the earth revolves around the sun, not vice versa. Now, remember, and we discussed this in class, he disagreed with Ptolemy on a very conservative manner. Copernicus still believed in epicycles, and that's because he could not account for the rotation of the Earth. But he is disagreeing with the church and with the norm when it comes to scientists and Catholics and Protestants and society as a whole when it comes to geocentrism. He also is arguing in his text that the further a planet is away from the sun, the longer it takes to revolve around the sun, relating, remember, time and distance. Okay? And what Copernicus is doing is his ideas and why they're so controversial is he's creating a lot of uncertainty with humans in the universe. Now they're starting to question things. Wait, you're telling me that everything I've been told before, everything I've been reading, everything I've been hearing is wrong? And so this creates a lot of uncertainty with Europeans, with society, and creates a lot of uncertainty with their relationship with God. And where does God fit in this picture? If it's wrong in the book of Genesis, of which you're stating, Copernicus, are other sections of the Bible wrong as well? Lots of uncertainty with people when it comes to religion. Okay? And then that is what he's doing. Copernicus is, in this hypothesis, that this idea of heliocentrism is directly challenging certain portions of the Bible, specifically the book of Genesis, and this notion that the earth is the center. Let us continue. And this is what he believed, and this is kind of his model of what his version of heliocentrism looked like. Okay, the sun being in the center Earth revolving, and the celestial bodies, the planets, revolving around the sun as well. Okay? Obviously, Copernicus is going to get confronted with religious attacks. Protestants really come hard at him first, well, because Copernicus is directly challenging a specific portion of the Bible. And we know from Protestants the Bible is their sole authority. So they are going to be very, very alarmed at Copernicus' ideas and attack him very, very viciously. Catholics will react as well, less forcefully because, well, the Bible, they don't interpret the Bible as strictly as Protestants do. Well, because the Bible is not their sole authority. A pope is, and we know this, but they will also join in on the attacks as well on Copernicus' ideas and condemn them. Okay? Another thinker that we have is Mr. Tycho Brahe. Born in Denmark, he was Danish. Super, super, super interesting. And he had one of the greatest observatories in the world, but the best observatory in Europe. And I have some cool pictures of that I would like to show you all. I went and visited it. It's just an incredible, incredible place and building. But Tycho Brahe's greatest contribution was not necessarily an idea, but that he was up in that observatory all the time, collecting lots and lots and lots and lots and lots and lots of data. Always graphing, always charting, always plotting, always observing and writing down what he saw. But Tycho Brahe's big problem was that he didn't know math. And so he had all this data, but he didn't know what to make sense of this data. And he didn't really know how to unlock this data. His assistant, Kepler, who we'll talk about next, is going to be able to. Kepler's going to take all this data that Tycho Brahe had and make sense of it. But Tycho Brahe himself could not make sense of it because he didn't know math. And what we're starting to see here, ladies and gentlemen, which is crucial, and the point I'm trying to get at, is we are starting to see the melding of science and math in the creation of physics. And that will come to fruition, that will really come into light with Isaac Newton, who's going to really, really make that solid with his theory of universal gravitation. Tycho Brahe did not believe in Copernicus' view. Okay, he did not support heliocentrism. He advocated for a more Earth-centered system. And Tycho Brahe specifically believed that Mercury and Venus revolved around the sun, but that the sun, moon, and other planets revolved around the Earth. So he believed in something different, in a more geocentric ideology. It was this a little different. He had a little caveat in his belief. But Tycho Brahe is really known for, ladies and gentlemen, what we need to remember for him is his data. Okay, and there he is right there, rocking the mustache, handlebar, connected to the beard. Whoa! Kepler is next, and Kepler was Tycho Brahe's assistant. And Kepler was a mathematician. He was really good at math, had advanced understandings of math, and he is going to be able to prove Copernicus' theory. Kepler is very famous for his 3 laws of planetary motion. Now, don't get this confused with Galileo. Galileo is going to start to come up with some laws of motion, like his law of inertia and his law of acceleration. Kepler is talking about planetary motion, and there's 3 laws that we got to know. Okay, and each law is going to be dealing with gravity and getting us closer and closer and closer to gravity. So I want you to keep that in your mind as well. So, the first law is that the orbits of a planet around the sun are elliptical and not perfectly circular. And ellipticals are more of an oval shape. And the reason, and he noticed this, and he was able to mathematically prove it. What he was missing was why and how. Okay, well, the why is going to be gravity. It's going to be gravity that's influencing this, because as we're seeing, planets revolve in orbit, the gravity of a sun versus the Earth, the sun has a greater pull of gravity, and that's going to be influencing the movement, speed of a moon or a planet. And so that he's noticing this law of planetary motion, but he's not quite certain of why and how, and that's going to eventually be built with and proved with Mr. Isaac Newton, Guzik's dude. Another law of planetary motion that we see, that a planet's speed increases as it gets closer to the sun, and we know why. Okay, Kepler didn't know, but Newton will eventually be able to tell us why, which is gravity, and that it slows down a planet slows down as it moves further away from the sun. And again, as you can see, we're getting closer and closer and closer to gravity. Okay, Kepler's last law was the time a planet takes to make a complete orbit is related to its distance from the sun. And again, this is again dealing with gravity. And so these are his three famous laws of planetary motion, and all kind of intermingling with this idea of gravity. Gravity plays a part in that, but Kepler doesn't know it quite yet. Okay, all right. So Copernicus, he was really speculated. He was putting forth this idea of heliocentrism. Kepler is going to be able to prove mathematically with all that data that Tycho Brahe accumulated. Okay, and so we're seeing kind of these thinkers build upon each other's ideas, and Isaac Newton will continue that with gravity. Okay, Kepler, is showcasing this relationship of a sun-centered solar system. He is further undermining Ptolemy and Aristotle's old system, and his third law of planetary motion almost proved the law of universal gravitation that Newton will. Okay, so we can see that Newton is going to take a lot of what he sees from Galileo, from Kepler, and he's going to. I think his famous quote is that it is only because I only see so far, or something along the lines of that, because I stand upon the shoulders of giants, and the giants that he is referring to are Kepler, Galileo, among other people. Okay, and there he is, Kepler. Okay, next up, you already know I'm gonna be playing some Bohemian Rhapsody in class with some Queen to talk about Galileo Galilei. All right, a mathematician. And that's important. That's an important fact about Galileo because, again, we're seeing mathematics play a really important role in science, and we're continuing to build up to modern physics. Galileo loved the telescope. He improved upon the telescope, and he is going to use the telescope to make his observations. And he's going to have lots and lots and lots of data with that telescope. And the only way he could make sense of his data, ladies and gentlemen, was by looking at his data through the lens of heliocentrism. But it was by using Copernicus's interpretation of the universe and using that interpretation in order to make sense of his data. It was the only way his data made sense to him. Okay, and he's going to help popularize Copernicus's ideas and system. Okay. Galileo, he began developing some of the first accurate laws of motion. Now, this is different. This is not planetary motion, of just universal motion. And there's two laws of motion that I really want to touch upon. One is acceleration, and another one is inertia. And so Galileo noticed that there was this universal force that produced a universal acceleration. Okay, and what he came across is that all falling objects descend with equal velocity regardless of weight. So whether you have an orange or a cannonball or whatever, they descend. If they drop, they descend with an equal velocity, and weight has nothing to do with it. Okay, before with Aristotle and other scientists previously thought that weight had everything to do with how fast something fell. Okay, but Galileo noticed that, if you put things in a vacuum, for example, there's no air resistance. If you put a feather and a, something metallic, a marble, in a vacuum, they will fall at an equal velocity, at an equal rate of speed. And that's because there's no friction, or there's no resistance that's inhibiting, that feather from, that would obviously affect an object of lighter weight from falling. So I guess the famous story about Galileo within this experiment and his idea here was, I guess he was on the Leaning Tower of Pisa, and he was like dropping objects off of the tower, and that's where he came up with it. I believe historians have debunked that claim. I don't believe it's true. It might be, I don't know. But again, this is dealing with his law of acceleration, that all fallen objects descend with an equal velocity regardless of weight. Okay. Another law of motion that he begins to construct is his law of inertia, movement. And prior to Galileo, scientists believed that that rest was a natural state for objects, that them staying stationary. But Galileo introduced a new perspective, and he states that objects only stop moving when a external force like gravity, like friction, something stops an object from moving. So for example, if I were to roll a soccer ball across our room and go wah, and just roll this soccer ball across the room, the floor, friction, gravity, so the floor from the bottom, friction, the wall would stop it, and then gravity would also be interacting with that soccer ball as well and eventually stop it. But if there were none of these external forces, that ball would just keep moving. That ball would just, keep going if there was no external force. So he argued that rest is not a natural state for an object, that an object in motion remains in motion until it's stopped by an external force. So quite interesting. So these laws of motion, acceleration and inertia, quite interesting. Okay? Galileo was also very empirical, meaning observant. And in the next couple lectures, we're going to talk about the scientific method using logic, empiricism, rationality, the inductive, deductive methods of reasoning. But Galileo liked to experiment on things. He didn't speculate what might happen. He experimented on what did happen. He didn't experiment, and he observed what he saw, and he wrote these findings down and used experimentation to find out new ideas. So he wasn't speculating on what might happen or if he did this. He actually did it. He actually experimented, and that's really important for the scientific method that we're going to continue to talk about in the next couple lectures. He's also famous for some of his discoveries with the telescope. He found a couple moons of Jupiter, and we're still discovering moons of Saturn, Jupiter, with the Hubble telescope. So I mean, it's pretty incredible that 300, 400 years ago, Galileo was doing this, okay, with not a lot of, advanced technology that we have today. He also discovered that the sun had sunspots, that the moon had craters and all kinds of mountain ridges, and it wasn't this smooth sphere, but it was actually kind of peppered with a whole bunch of inequalities, as he called it, and that was because the moon has no atmosphere, so if an asteroid hits it, it's not going to burn up, it's going to go boom! The planets are not embedded in these crystal spheres, and that Earth is made up of similar materials as what he was seeing out in the heavens, and he was arguing that the Earth is made up of the same stuff that you see in space, and he was arguing for that. Okay, and he supported Copernicus' theory. Okay, very much so, of heliocentrism. And there is Mr. Galileo, looking serious. All right, religion and science. Obviously, this is where Galileo is really, really, really famous, really important, as we see this fight in this tension between religion and science. And eventually, as we go throughout this class, we are going to see the world become more secular. We are going to see a secularization of the world that continues. And, it takes even another leap during the 1800s, during kind of a second scientific revolution, with Darwin, and we see the church be put on its heels again. But we are seeing religion start to slowly give way to science. Galileo was friends with the Pope, and the Pope actually allowed Galileo to discuss heliocentrism and Copernicus' theory within his text. Galileo's famous book is called The Dialogue of the Two Chief Systems of the World, written in 1632. And this is where he defended Copernicus and where he disagreed with Aristotle and Ptolemy. Now, what got Galileo in trouble was not his belief of heliocentrism. It was how he said it. In his Dialogue of the Two Chief Systems of the World, I have not read this book, but according to the church, he was very condescending and arrogant and not very nice. And that got the church quite upset. Really, the Pope upset and salty, and they are going to try him for heresy and as a heretic for his beliefs. And he was put under house arrest. He was threatened with torture, and he was forced to recant. Now, I guess the story about Galileo is that when he was forced to say, okay, Earth is the center of the universe. I was wrong. I've been wrong this whole time. Underneath his breath, when he walked out of his courtroom during his trial, he muttered underneath his breath, and yet it moves. and yet it moves. And he was referring to the planets. And so he was kind of just saying like, all right, I'm gonna tell you all these things and say I don't believe in my ideas, but he actually still did believe in his ideas. Okay. And this trial, really symbolic of the conflict between religion and science. Sorry, I forgot, between religion and conflict. No, it should say religion and science. This is a symbol of that conflict between the two. And, in 1992, the bell's ringing. Class is starting. No, I'm just kidding. I'm at work on a Friday and there's no school. So, this trial is really a symbol of that, of the conflict. And, recently in 1992, when I was the ripe age of 3, the Catholic Church admitted that they were wrong, and I believe they acquitted him. I'm not too sure on that, but I believe that they admitted that they made a mistake with Galileo. Okay, all right, let's talk about Mr. Isaac Newton. Super important, ladies and gentlemen. English. He's one person I would love to meet in history. And just perhaps one of the greatest minds society's ever known. And he is going to answer that question of how planets move in an orderly fashion. Why is there this universal acceleration? Why do planets move in an ellipse? Why do planets speed up as they get closer to a sun, and decrease in speed as they get farther away? He's going to give them the why, and it is his law of universal gravity. Okay, and he was going to address these complicated issues that Kepler and Galileo quite couldn't get to. And he was very, very, very much influenced by Galileo's focus on math. His text that he wrote many of his ideas, and we've got to know this text, is called the Principia, otherwise known as the Mathematical Principles of Natural Philosophy, considered by many to be the greatest book on science ever written. And Isaac Newton in this text is melding science and math and putting it together. And this is, considered the first modern physics book. And he's presenting a framework to look at the world not religiously, but look at the world mathematically. Look at it rationally. You can figure things out with math. You can figure these scientific questions out with math. And he's going to be doing that with his law of gravity. All right. And in this text, so important, so incredible. He's laying the foundation of physics, and he is also proving a lot of his ideas within this text through a new type of math that we are seeing for the first time called calculus. And that is just incredible. I mean, he is helping invent calculus. Just absolutely just phenomenal, okay? So, he is further improving upon the laws of motion, but what he is most known for in this Principia is his law of universal gravitation. And he is explaining how gravity works, how physical objects move in the universe in an orderly fashion. And it is through this idea of gravity that everything in the universe attracts another body in the universe. And like if you're having trouble understanding gravity a little bit, I can go into more depth in class and kind of go through that. But he is explaining how gravity works and how it interacts with physical objects to move in such an orderly way. Like, why does the moon not just fly off, woo, or why does the moon not crash into Earth? And why does the Earth, go around the sun in 365 days in this uniform way? And that is gravity. And he's able to prove it with math. He's not just stating it. He is proving much of what he is saying through math. Now, it's a little asterisk when it comes to his findings. He's not proving necessarily the nature of gravity, aka like what makes up gravity and what forms gravity. He's just merely mentioning how gravity is interacting with physical objects and how it works. And he's using math to do that. He's doing this empirically, aka through observations, using math, reason, and logic. And he's explaining all of this, which is incredible. This is brand new. Without God, he's able to prove much of this without using any type of religion, which is brand new, which is foundational and creates a lot of uncertainty. He is able to account for all of these things without religion, which is brand new and foundational and very important for further science and further discoveries. So this is Mr. Isaac Newton and his laws of gravity within his important text, the Principia. Okay, and there he is, rocking the wig. Woo! All right, we'll stop here for today.